Okay, welcome viewers. In today's video lecture, we want to cover various topics. Okay, so one by one, we talk about these topics. Like question one is this: find the greatest element and least element. Okay, uh, see, we have this diagram: A, B, C, D. Okay, see, greatest element is that element uh, which such that every element has relation with that element. Okay, now you see that you cannot say here that B is the greatest element because this C has no relation with B. Okay, similarly we cannot say that B is the greatest element because B has no relation with C. Okay, and D, this cannot be said as greatest element because B and C, they do not have any relation with D. Okay, so greatest element is that element such that every other element has a relationship with that element. Okay, so here we say that greatest element does not exist. Okay, now least element is that element which maintains the relationship with all other elements. So you see that A, it is connected with B, A, it is also connected with C, so A, it is also connected with D. So A maintain a relationship with all the other elements. Okay, so the least element is A. Okay, the least element of this diagram is A. So here greatest element does not exist, whereas the least element of this exists. Okay, now next problem. Next question is this: suppose we have this diagram. Okay, here you have D, E, C, A, and B. Okay, see, the greatest element whenever it exists, it is always found at the top of the diagram. But you see that D cannot be said as the greatest element. Why? Because E has no relation with the D. Okay, and similarly E cannot be said as the greatest element because D has no relation with E. Okay, so here we say that greatest element does not exist. Okay, now likewise you check uh, uh, least element it is always found at the bottom of the diagram. But you check that A has no relation with B. Okay, whereas A has relation with C, E and D, but A has no relation with B. Okay, because there is no line joining with B. Okay, so and similarly B has no relation with A. So least element does not exist in this case. Okay, now next we see. So next we have this diagram: D, C, A, B. Okay, so you see that D is the greatest element. Why? Because A has, see, A has a relationship with D. Okay, see, A is connected with D. Similarly B, it is also connected with D. Okay, similarly this C, it is also in connection with D. Okay, So here the uh, greatest element, greatest element, it is what? It is D. Okay. Now least element. I told you in the beginning also that least element, it is always found at the bottom of the diagram. But you see that as A has no relation with B and B has no relation with A, so least element here does not exist. Okay. Now next next problem we now see. So the next question is that we have this diagram D, B, C and A. Okay. So you see that greatest element. See here, this C has a relationship with D. This B has a relationship with D. A also has a relationship with D. Okay, A also has a relationship with D. So the greatest element is what? It is D. Okay, least element, least element. Okay, you see that this element A, it has a relationship with B, with C. This A has also a relationship with D. Okay, so it means that this A maintains the relationship with all the other elements. So that is why the least element of this is A. Okay, so here greatest element and least element both exist. Here you people note down one more thing, that whenever greatest element and least element exist, then they are always unique. Okay, so this thing you always remember, that whenever greatest element and the least element they exist, then they are always unique. Okay, now next we want to talk about comparable elements. Okay, so next definition is the definition of comparable elements. So what are comparable elements? Okay, the elements A and B of a coset, okay, mean partial order set, S under less than or equal to, are called comparable, if A is less than or equal to B, mean A is in relation with B, or B it is in relation with A. Okay, if neither A is in relation with B nor B is in relation with A, then elements are not called comparable elements. Okay, so here this symbol, okay, it may change question to question. You may have less than or equal to symbol, or you may have divisibility symbol. Okay, according to that, solve the problem. So question is this: check in the poset, in the poset Z plus under divisibility. Number one, 3 and 9 are comparable. Number two, 5 and 7 are comparable. Okay, so this we want to check that these elements are the comparable elements or not. Okay, so see the solution. Clearly 3 divides 9. Okay, see, relationship is the relationship of divisibility. So clearly 3 divides 9. Okay, it means that this element is in relationship with this element. Okay, and what is the definition of comparable element is this, that if A is in relation with B or B is in relation with A, then we say that elements are comparable. So here clearly 3 is in relationship with 9. Okay, so it means that 3 and 9 are comparable. Okay, now next, second part, neither 5 divides 7 nor 7 divides 5. Okay, neither 5 is dividing 7 nor 7 is dividing 5. It implies that 5 and 7 are not comparable elements. Okay, these elements, they are not comparable. Okay, I hope you people have understood this thing. Okay, that how to check elements are comparable or not. Now next we want to find upper bounds. Upper bounds, before starting this topic, upper bounds, here I would like to tell you about the Toset. Okay, in a poset, if every pair of elements are comparable, then it is called a Toset. Toset means totally ordered set. It is also called a chain. Okay, so see the example of this. uh, Question is this: check this set 1, 2, 4 and 8 under divisibility is a toe set. Okay, so we want to show that this is a toe set. So solution, what you do, you need to first of all check that every element, are they comparable or not. So we make the Hasse diagram of this. Okay, so first element is 1. Okay, now what is the relationship here? Relationship is the relationship of divisibility. So clearly 1 divides 2. Okay, 1 divides 2. So in hierarchy 2 should come after 1. Okay, next 2 divides 4. Okay, so clearly 1 also divides 4. Okay, next 4 divides 8. Okay, 2 also divides 8, 1 also divides 8. So it means that if you take any pair of elements, then there exists relationship between them. Okay, see, for example, if I select 2 and 8, then clearly 2 divides 8. If I take 4 and 8, then clearly 4 divides 8. If I take 1 and 8, then clearly 1 divides 8. Okay, so take any pair of element. Okay, they are related. Okay, so every pair of elements are related. Okay, therefore it forms a Toset. Okay, so in this way we can prove that it is a Toset. Whenever every pair of elements they are comparable, or we can say that they are in relation, then it forms a Toset. Okay. Now next we want to talk about upper bounds, lower bounds. Okay. uh, Greatest lower bound, greatest lower bound, which is also called GLB, and least upper bound, which is also called LU. Okay. Now we next want to find all these four type of elements. Okay. Now for this, consider this question. Consider D100 under divisibility. D100 means divisors of 100 is a Toset. Find upper bounds, find upper bounds, comma lower bounds, comma LUB and GLB. Okay, so we want to find all these elements in a D100. Okay, so you see the solution. D100 means divisors of 100. So which elements come in this set? 1, 2, 4, 5, 10, 20, 25, 50 and 100. Okay, these are the divisors of 100. Okay, now next we draw the Hasse diagram. Okay, see, first of all you take 1. Clearly 1 divides 2. Okay, but 2 also divides 4. Okay, 2 divides 4. 1 divides 5. 1 divides 5. Okay, so the next element is 10. So 5 divides 10. Okay, but 2 also divides 10. Okay, next 4 divides 4 divides 20. Okay, the next element is 20. So 4 divides 20. Okay, here you take 20. Okay, 4 divides 20, but 10 also divides 20. Okay, next element is 25. Okay, so 5 divides 25. Now next element is 50. Okay, so here you take 50. So 10 divides 50. Okay, and then the next element is 100. Okay, next element is 100. Okay, you see here one more thing, that 25 also divides 50. Okay, next element is 100. So 20 divides 100 and 50 also divides 100. Okay, so this is the Hasse diagram of D100. Okay, now we want to find upper bound, lower bound, GLB of this set. Okay, you will always be given one set according to which you have to find all these things. Okay, now first of all we find upper bounds. Okay, upper bounds, upper bounds of 5 comma 10. Okay, by upper bound of this set mean that find those elements in this D100 set. Okay, which are divisible by both these elements. Okay, I repeat, uh, by finding upper bounds we mean that find those elements of D100 which are divisible by 5 and 10. Okay, So you see that the very first element which is divisible by 5 and 10 is 10. Okay, so write down here 10. The next element which is divisible by 5 and 10 is 20. Okay, next element is 20. Okay, you cannot take 25 because 5 divides 25, but 10 does not divide 25. So do not take this element. Okay, the next element is 50. Okay, because 50 it is divisible by both 5 and 10. Next element is 100 because 100 is also divisible by 5 and 10. Okay, now out of all these upper bounds, okay, which one is least? Okay, LUB. Okay, which one is least? Least mean this number is the least one. Okay, among all these upper bound, which one is least? Least one is 10. Okay, so LUB is what? It is 10. Okay, now lower bounds. Lower bounds of 5 and 10. Okay, by finding lower bound mean that from this D100 find those elements which divides the elements of this set. Okay, from D100 find those elements which divide 5 and 10. So the very first element which divide 5 and 10 is 1. Okay, 1 divides 5 and 10, but 2 does not divide 5. Okay, so 4 does not divide 5. Next element is 5. Okay, next element is 5. So only these are two elements which divides 5 and 10. Okay, which divides the element of this set 5 and 10. Now which one is the greatest? Okay, greatest lower bound. So the greatest one you can see from here, the greatest one is what? It is 5. So this is the answer of the problem. Okay, so in this way, whenever you are given one set, okay, and you are given another set with respect to which you want to find the LUB GLB, so we can easily find it like this. Okay, now next we want to talk about lattice. Okay, that what is a lattice? Okay, lattice. Lattice. So a partially ordered set in which every pair of elements has LUB, mean least upper bound, and greatest lower bound is called a lattice. Okay, uh, a partial order set in which every pair of element has LUB and GLB, it is called a lattice. Okay, so you here remember one thing, that if operation is divisibility operation, then for finding LUB, okay, mean if you take two element and we want to find the join of them. Okay, so it means that take the LCM of A and B. Okay, and if you want to find meet, this symbol means meet, in that case find GCD. Okay, but when do we find LCM and when do we find GCD? When the operation given is the operation of divisibility. Okay, otherwise we do not use these operations. Okay, now next, if the operation is subset operation, if the operation is subset operation, then A join B mean take the union of two sets. Okay, and A meet B mean take the intersection of the two sets. Okay, so in this way we find the LUB and the GLB. Okay, so we now solve the question. So see the in order to prove the lattice, the thing is this, that if the GLB, okay, means supremum and infimum, both exist for every pair of element in the same set, okay, in the same set, then only we say that it is a lattice. Otherwise it is not a lattice. Okay, so we now see that some examples in which we see that which examples they form a lattice and which they do not form a lattice. Okay, so the question is this: determine determine whether the poset the poset 1, 2, 3, 4, 5 under divisibility and 1, 2, 4, 8, 16 under divisibility are lattices or not. Okay, so you see that what is the definition of lattice? If for every pair of elements supremum and infimum exist, okay, supremum mean LUB and infimum mean GLB, okay, only then we say that these are lattices. Okay, so it should happen for every pair, and if it does not happen for even a single pair, then we say that it is not a lattice. Okay, so what you people do now, you directly take those elements, okay, for which LUB and the GLB they do not exist. Okay, uh, so suppose that for the first set I take 2 and 3. Okay, take 2 and 3. Okay, let me call this set as S set. 1, 2, 3, 4 and 5. Okay, take 2 and 3 from this set S. Now what is the join of these two elements? You were told whenever the operation is the operation of divisibility, in that case you find the LCM. Okay, so what is the LCM of 2 and 3? LCM of 2 and 3 is 6. But 6, this is not the member of S. Okay, mean if supremum here it is 6, but it is not the member of S. Okay, and in order it to be a lattice, this should be the member of S. Okay, but this is not the member of S. Okay, hence we say that, hence it is it is not a lattice. Okay, now we now check this for this set. Okay, let me call this set as A set. A set is 1, 2, 4, 8 and 16. Okay, now suppose you take any two elements, suppose I take 2 and 8. So what is the GCD of 2 and 8? It is 2. What is the LCM of 2 and 8? It is 8. Okay, now suppose I take 4 and 16. What is the GCD? GCD is 4. And what is the LCM? LCM is 16. So 4 and 16 they are again the member of this set. Okay, now suppose I take 1 and 16. Okay, so what is the LCM of 1 and 16? It is 16, and it is the member of A set. And what is the GCD? GCD is 1, which is again the member of this set. So here I have checked that for every pair of elements, supremum and infimum exist in the set. Okay, so here we say that for every pair of elements supremum, or you can say LUB and GLB exist, therefore it is a lattice. Okay, it is a lattice. Okay, so this thing you always remember. Okay, now next we want to talk about next we want to talk about sub-lattice. Okay, sub-lattice, it is similar, okay, to lattice, but here if the subset of your given lattice it becomes lattice, okay, then we say that it is a sub-lattice. Okay, so definition is this: sub-lattice. Okay, let S be a non-empty subset of a lattice L if S is itself a lattice, then S is called a sublattice. Okay. Uh, so the diagram of this goes like this: that suppose here you have lattice, and S is what S is the subset of L. Okay, and if S is itself a lattice, means if the supremum and the infimum of every two pair of elements exist in S, then we say that it is a lattice. Okay, and as it is a subset of L, so it becomes a sublattice. Okay, so we now see example of this. Okay, so the question is this: consider this set 1, 2, 3, 6. Okay, under divisibility. Okay, then this set is a lattice. Okay, mean it is already given that it is a lattice. Okay, now I take two subsets of this set. Okay, suppose I take first set as this 2 and 3 under divisibility, and I take another set as 1 and 6 under divisibility. Okay, check check these are sub-lattice or not. Okay, so we want to check that these are sub-lattice or not. Okay, see, if the supremum and the infimum both exist in the same set, only then we can say that it is a sub-lattice. Okay, so see, what is the operation? Operation is the operation of divisibility. So I take these elements 2 and 3. Okay, so take 2 and 3. Now what is the join of 2 and 3? Join of 2 and 3 mean take the LCM of 2 and 3. So what is the LCM of 2 and 3? It is 6. Okay, so 6 is clearly, it is not the member of this set. Okay, it does not belong to 2 and 3. So clearly LUB, it does not exist. Okay, clearly LUB does not exist. Okay, so therefore it is not a sub-lattice. Okay. Now, next we want to check it for this set. Okay. So we now check it for this set. Now, solution. Here you have two element 1 and 6. Okay. Now, what is the join of 1 and 6? It means that the LCM of 1 and 6. So, what is the LCM of 1 and 6? It is 1. Okay. And what is the, LCM of 1 and 6 is 6. Okay. And this is the member of this set 1 and 6. And what is the meet of 1 and 6? Meet means GCD. GCD. Okay. GCD of 1 and 6. So, what it is? It is 1. It is again the member of 1 comma 6. Okay. So you see that supremum and infimum both exist for these elements. Okay. For this set. Okay. So we can say that this is a sub lattice. Okay. This is a sub lattice. So this is all about this. Okay. So you